Okay, so last time we were talking about line integrals, specifically vector line integrals. Remember, there are scalar line integrals and there are vector line integrals. Very often those terms aren't distinguished. I think they should be, right? So you're going to hear me say vector line integral. A lot of people just say line integral. Here's I think kind of the best overall, if you had to pick one notation for vector line integrals. It's simple to write down, requires less pencil lead than the other bits of notation we have to choose from. It very naturally connects to the idea of computing work. That's one of our big applications. Very natural in the sense of force dot displacement. You can see it right there, right? So that's nice. And I also like to think of it as being geometrically natural. So what I mean by this is that this is telling you about the domain, right? I mean, everything that you want to know about a little piece of the domain as relates to the whole chop it up, add it up strategy, the dx vector encapsulates all of that information. Okay. But we have these other notations, right? So let's see, let me go at these maybe a little more slowly. So dx, I can rewrite two different ways. That gives me a couple of different alternative notations. The book actually likes this one more, which is fine. This one here is if you want to compute directly from a parameterization, right? Very often you do. Not always, but very often. Then that's a very handy way to think about vector line integrals. On the other hand, this one, and let's not forget, by the way, that dot product with a unit vector gives you a component, right? This one, cosmetically, if nothing else, kind of looks like a scalar line integral, right? So this is a point of view if you wanted to argue that, look, come on, they're all line integrals, this would be a way to make that case. Counter-argument, of course, is that this then is no longer a function of only position. This also depends on the curve, this tangent vector. That comes from the orientation of the curve. It's not, it depends on how you look at it. I don't feel like it's part of the integrand myself. To me, the integrand is stuff that's independent of the domain. But anyway, and also, this point of view, very natural to relate to the idea of fluid flow. Remember, vector fields can represent lots of things. Vector fields are not a single physical concept. Vector fields can represent forces, sure, but vector fields can also represent flows of fluids or flows of things that kind of behave, at least in some sense, like fluids. If you want to make sense out of a vector line integral while you're thinking about fluids and not forces, then this is a great sort of foot in that door. And then lastly, real quick, we made this argument about how, our displacement differential dx, it does have components, which very naturally you might want to call that. And our vector field has components. You very naturally might call it p, q, and r. And so this integral, if you kind of work out the dot product, it's kind of natural, at least in some sense, to write it like that. And we've already kind of talked about that notation. So be aware of all these different notations. They're out there, right? And they have their uses, all of them. And so you can't just pick one, this is the one I'm going to use, and then ignore all the others. You kind of have to be aware of all of them. Okay. All right, so we're going to go on now. Next thing, we're going to talk about something called the fundamental theorem of line integrals. Sounds important. Fundamental theorem and all that. So by the way, we're going to be doing a bunch of different theorems in Chapter 15 going forward. There's lots of little asterisks that really should be put in about, if the vector field is differentiable, continuously differentiable, this thing needs to be continuous. There's certain just little nitpicky little details that really should be considered, and we're going to ignore all of that in this discussion in Math 212. There's enough going on without those worries, right? So don't let me leave you with the wrong impression that these things don't matter. It's just I'm going to kind of tack them on at the end. The book, puts them, correctly in, as the conditions of the theorems. But worrying about why on those things is really, I feel not really part of Math 212. Okay, so this is my get out of jail free card on lack of rigor issues. Okay. All right. So to talk about the fundamental theorem of line integrals, I'm going to first do a flashback to the fundamental theorem of calculus. Before I do, let me tell you why. And that is that they're very similar theorems. They have a lot in common. Now, why are they similar? Why do they have a lot in common? And it turns out that there's a deep reason why these two theorems have a lot in common. And that is these theorems, the one that you know and the one that we're about to learn about, they're both special cases of a single larger theorem. There is a single larger theorem that, if n equals 0, and you get the fundamental theorem of calculus, and if other condition, then you get the fundamental theorem of line integrals. So they have a lot in common because they're kind of the same theorem, just applied in different contexts. Right? Now, here the bad news about that fact is that I can't tell you the big theorem, right? The big all-encompassing theorem that of which these are special cases. It's too deep. It's too sophisticated and hardcore and advanced. And so in Math 212, I will not talk about. I'll tell you the name of it. It's called the generalized Stokes' theorem, right? And it's just too much, right? So even though I can't talk about that theorem, though, the fact that it exists has important consequences for us in this course. And there's a couple that I'll point out. One is because this big theorem exists, even though we won't talk about it, there are strong analogies between these two theorems. We will see those analogies. I do expect you to understand those analogies between these two theorems. There are also, what we're going to find, connections between these two theorems. It's not just that they're kind of like each other, but these two theorems and other theorems that we're going to talk about relate to each other. You can use one to talk about another, and they just really they interconnect in a lot of complicated ways. And that's going to be a really big deal. That is computationally important. It is important for understanding the theorems to see how they connect to each other. And there's lots of applications of the fact that these theorems all connect to each other. So we're going to see lots of shadows of this large theorem without actually seeing the theorem itself. Okay. Oh, by the way, and I should also mention that in addition to these two theorems, both special cases of the generalized Stokes' theorem, there's also something called Green's theorem, and there's something called Gauss's theorem, and there's another version of Gauss's theorem, and then there's what's called Stokes' curl theorem, which is another special case that historical reasons named after Stokes. Really all of these theorems are all special cases of this one theorem, and they're therefore all have connections between them and analogies between them. And again, we're going to see a lot of that as we go on through the course. Okay, so that's just context. I wanted y'all to sort of know what's coming. So why I'm talking about the fundamental theorem of calculus again is to set up the pattern. Right, we're going to see a pattern repeat over and over again as we talk about these new theorems. The pattern is visible in a very natural point of view on the fundamental theorem of calculus that you all know. So I am not doing this flashback to remind you of Calc 1. Right? I assume that y'all already know the Calc 1 point of view on the fundamental theorem of calculus. I want to give you a different point of view that will allow me to sort of make connections to the later stuff we're going to do. Okay. So we tend to think of the fundamental theorem of calculus as a way of computing integrals. I don't want to think about it that way. That's already weird. Right? I want to think about it as a way to compute change. Seems like a lot of trouble to go to, right? If I want to know the difference between f of A and f of B, how about you just subtract? Wouldn't that be easy, right? But weird though it may seem, unnatural, counterproductive though it may seem, I'm going to try to understand change as an integral. Okay, so first observation to make is that change is an accumulating quantity. Now, we've used this word before. Let me remind you where we've used this word before. Let's consider an application of you got a one-dimensional rod, right, made out of some inconsistent alloy where there's more iron on this side, there's more aluminum on this side, whatever. If you want to compute the total mass on that one-dimensional rod, you chop it up, add it up, right? You chop it up into little pieces, and the accumulation feature of mass is that when you chop it up, the mass of the whole is the sum of the masses of the individual pieces. That's how mass works, right? And that's how a lot of things work, right? Chop it up, add it up, applies very broadly in lots of different, we've seen many examples earlier on, right? But I want to point out that it doesn't work for everything, and it does work for mass. And the weird thing about it is it also works for this very non-physical thing called change, right? So change is, again, this expression, how much does some function, what's the difference in the values of the function? Well, change accumulates. I can write it like this. The change over the whole interval, if you have some function, whatever that function may be, the change over that whole interval is the sum of the individual changes that the function makes over little intervals. Now, it's like I say, a weird thing to observe, but you got to give it to me. It's true, right? If you want to keep track of, between time equals A and time equals B, you want to keep track of, how much did your height change? Something like that, right? The total amount that your height changes, well, it's the sum of how much did your height change on the first day, plus how much did your height change on the second day, and it adds up. I mean, that's how it works. So a modest observation, really, but also counterintuitive. I mean, again, this word accumulation, we've been thinking of it as something that applies to stuff, to physical things, mass, ants, right? Work, I guess, is maybe less concrete physical, but still kind of physical, right? And now I'm thinking of this as something that applies to an algebraic expression. So that's a little weird, but it's going to be an important concept. Okay, all right. So this is true for all values of n. No matter how you slice it, change accumulates. So if I take the limit as n goes to infinity, the expression is the same for all values of n, so take the limit all you want. You're taking the limit of a constant, right? So, of course, the limit's equal to that value. Okay, so this is starting to look like an integral. Not exactly. I need to have, of course, a delta x on the end to make that look like a Riemann sum, aka integral. Of course, you can't just stick stuff on because you need it. You've got to be legal. What is legal is that I can multiply and divide by the same thing. Perfectly legal. Right? And now you see it really starting to look like an integral. Big question is integral of what? And here's another place where I'm going to sweep rigor under the rug, and it's fine, and don't worry about it. It's not what this course is about. But you can take this limit and pass it inside the summation. And the limit of delta f over delta x, of course, is f prime. By the way, let me, just for the record, lucky break. Just happened to be that this integrand, this brand new integral that we're developing, the integrand just happened to be an expression that we already know. That's unexpected. It's also not going to continue to happen, right? When we do make arguments like this coming up real soon, it's going to not be a familiar expression, and we'll talk about how to deal with that later. Okay. So here's our theorem then. Now again, that's the fundamental theorem of calculus. Y'all all know this theorem, right? But we're thinking of this now as a different way. We're thinking of change as accumulating. It accumulates over this interval from A to B. And the way that it breaks down as an integral is as an integral of f prime. Now, a reminder, we have seen accumulating quantities computed with integrals before. We saw mass as an accumulation of little pieces of mass, and we wrote down mass as an integral integral of density. Density might be a function of position, right? And so let's look at just, for semantical sort of motivations. We call this mass density because it's a density. It's an integrand, something that I multiply by size, associated to a computation of mass. It is very reasonable to call that mass density. Well, look, hey, just following the pattern, right? By analogy, this thing, well, it's the thing that I multiply by size in a computation of change. So if you're going to call delta mass density, I think it's a modest proposal that we should call the derivative change density. And I know it's weird. Right? You've got a lot of different ways to think of the derivative. Slope of a tangent line, a fraction of differentials, a factor that, what do you multiply by input changes to get output changes? Velocities. There's different ways to think about derivatives in different contexts. I'm going to add to that list. I'd like to encourage you all to start thinking of it as a density. Because, again, a reminder, this theorem is the first of several. And in those several theorems, it's going to be important to think of the integrands as density. Okay, so the better you can think about this integrand being a density, the more sort of geometric sense and geometric comfort that you have with the idea of thinking of that as a density, the more natural it's going to seem when I start needing to do the same thing in other contexts that are going to look very different. Okay, alrighty. So with all of this in mind, let's now try to apply these same ideas to a multivariable context. So let's suppose I have a curve, and the analogies are crazy strong. It's just weird how everything falls into place pretty much the same way. Suppose I'm interested in change. That's reasonable. Maybe this is a mountain road, and I want to look at how much my altitude changes between this point and that point. I mean, very natural thing to want to ask about. Or maybe I want to see, how cold is it going to be up there at the top of the mountain? Well, okay, I want to know how much temperature changes. Change is a really natural thing to want to keep track of. Okay. Well, change still accumulates. Again, that's the same reasons. Little bits of change add up over time to give you a total change, right? I mean, it's right there in the language. It's an additive thing. And again, we can kind of rewrite the whole thing. I can take a limit for free. That's fine. Now, I'm going to make a slightly different version of the argument here, but this is a Chapter 13 fact. So I'll refer you back to Chapter 13 for this. But the gradient vector is the relationship between input changes and output changes. Right? So this is one of the versions of that idea. Derivatives, a relationship between input changes and output changes. Specifically, f of b minus f of a is approximated by gradient dot change in the input. For your flashback purposes. And that being said, note that here we are again. We have a theorem. If you're interested in computing change, it's in fact a line integral. Right, so reminder, this is our very definition of a vector line integral. Going back to the beginning of yesterday's talk. Okay. So now again, I motivated this theorem that way, right? I started this as, hey, how would I calculate change? Answer an integral, but probably not a big surprise. The way we're going to use this theorem very often is like this. If you find yourself interested in computing a vector line integral, and if you don't want to have to parameterize the curve and plug it in and do the dot product and take an integral and all that stuff, magic formula for computing it. Yeah? Everybody okay? Got examples and details all to follow. But so big picture, you notice that this is following a lot of patterns that we talked about with fundamental theorem of calculus, right? We started with change, we motivated an integral. In practice, we tend to use this as a tool for computing integrals, etc. Okay. Oh, then there's the business about densities. Okay, can I interpret this as a density? And that it's it is a little bit different, a little bit weird. We tend to think of density as stuff per unit size, namely you take a quantity of stuff and then you divide by a size. Here size is, well, the thing that the gradient pairs with isn't really a size, right? It's a vector. So it'd be not quite correct to think of gradient as being a density in that sense, but it does have some things in common. So one way you can think of the gradient then, right, there's what the gradient is. There's the gradient, right? You can think of the differential as having a direction and a magnitude. Note then this is a thing that you're multiplying by size, right? So gradient dot unit vector is a density. The gradient itself isn't. Another way to think about this same thing, I could rewrite the gradient vector itself as magnitude of the gradient times the unit vector pointing in the direction that the gradient points. And then we can look at, dot dx. Right? And you can think of the magnitude of the gradient as kind of being it's kind of a density in some sense. That's change per unit distance in some hypothetical scenario where you're moving in the direction of the gradient vector, which you aren't, right? And then you can think of the unit vector part of this as being a correction factor. In fact, let me circle this. Dot product with the unit vector, that's the correction factor that tells you, okay, the magnitude of the gradient is in some sense the optimal density. It's optimal change per unit distance. And dot product with the unit vector tells you how much of that you're actually experiencing as you're moving in the direction you're actually moving. So anyway, so you have to kind of tweak around and play with it to recover the idea here. But one way I like to think of it then, I wanted to keep that. One way you can think of it then is you can think of the gradient as being sort of an oriented density. So oriented in the sense that there's a direction correction factor, right? But then in the optimal direction, that can be thought of as a density. We'll talk more about that later on. This idea of an oriented density is going to come up later in another theorem. So we'll talk about it more then. Okay, so how do we actually, again, use this theorem? This seems to suggest I can use this for computing vector line integrals. Sweet. Right? Computing vector line integrals is, you got to parameterize and you got to take a derivative and you got to do dot products and integrals and there's a multi-step and it's tedious. So can you, thing about it is, certainly the fundamental theorem of calculus, we did that a lot. Right? You got to be able to find the antiderivative. It's got to actually be an antiderivative of something, and then you've got to be able to find that antiderivative. Everything is an antiderivative in single variable calculus. Every continuous function is an antiderivative. It's a big problem in single variable calculus is how do you find the antiderivative? So the first thing I want to point out here is this is not analogous. It remains, I've got to be able to find not an antiderivative. I've got to be able to find the function. I've got to find the thing whose gradient is my integrand. So I've got to be able to find the anti-gradient, I like to call it, right? But unfortunately, it also has to, of course, be a gradient of something, right? So not everything has an anti-gradient is the punchline I'm coming up to. Even though everything has an antiderivative, every continuous function has an antiderivative, not every vector field, not every nice vector field even has an anti-gradient. So that's something we're going to have to watch out for. But that's a worry we'll worry about in a little while. Let's get our hands dirty and do one. Reminder. Here's what we're looking at. If we want to compute a line integral, Cool, there's your formula. Let's do that. Suppose I want to compute this line integral here. This line integral here. Suppose my vector field is given. Suppose my curve is given and in fact pre-parametrized for me. Before today's lecture, what would we do to solve this problem? Well, we take a deep breath, right? And we'd take that parameterization and we'd plug it in, and we'd have to compute x prime as part of the dx vector, so I'd have to take a derivative of this ugliness, right? And then furthermore, I would have to take this formula for z and plug it in there. So that's going to be part of my integrand. Yay. Right? And then I would have to take this ugliness, because that's y. I'd have to plug that in. So that's going to be part of my integrand too. And you can see this coming. I would have an ugly integral to work out. From 0 to 1. Right? But there's a, I mean, just think about what kind of a beast that would be, right? It's highly undesirable. And it would work out, and you could do it that way, but it would be a bummer, right? So what we're going to do to avoid all of that work, we're going to make the observation that this integrand is, in fact, a gradient. This is what I like to call the anti-gradient. By the way, that term is, the book doesn't use that term. The book uses a different term that I'll talk about later. I think anti-gradient is the natural term to use. I mean, we use anti-derivative to mean the thing whose derivative is what you started with. So I would like to use anti-gradient for the thing whose gradient is what you started with, right? I think it's very reasonable notation. So anyway, I'm going to say that a lot. Okay. So there's the anti-gradient, easily checked, right? Take its gradient. Easy partial derivatives. There it is. Totally works. Easy thumbs up. I know what you're going to ask. You're going to ask, where did I get this from?
Sort of, yeah.
Yeah, okay. All right. I'm going to totally get to that. But can I blow you off? And we'll totally get to that in a moment. Yeah. So there's my anti-gradient. Curtain to be pulled back on the magic trick later. Right? Then it's a plug and chug at this point. Right? Starting, there's my anti-gradient that I plug into. The starting point of this curve is where t is equal to 0. Here, let me do this better. Let me do this here's my curve. There's my parameterization, right? So plug in t equals 0 to get my starting point. Plug in t equals 1 to get my ending point. Notice what I have written down here is just straight out of the theorem. An integral of a gradient is f of b minus f of a. I mean, I'm just copying at this point from the fundamental theorem of line integrals. It's all arithmetic from here, and there you go. So we just computed a vector line integral with a minimal of effort. It's pretty cool, isn't it? Now, I think it's a helpful exercise. I want everybody to do this, at least until you're highly persuaded of the moral. But I want you to take this and directly plug these into that and see if you were to do this the brute force way, right? If you were to go straight from the parameterization, a la Wednesday's lecture. See how ugly that would be, right? And again, as soon as you get that written down, I think you're going to be like, oh gosh, I really like this now, because of what it saves you. Okay, all right, okay, Now, so this was a deliberate little performance. I wanted to be dramatic. I wanted y'all to see how nice the fundamental theorem of line integrals is and how it saves you all this effort. Look how easy. My gosh, it was plugging in. It was triviality, basically, right? The fundamental theorem of line integrals as soon as we realize that our vector field is a gradient of something, then all I have to do is a little bit of arithmetic and bam, we're done. Right? Okay, now, so let me confess, again, for dramatic purposes, I like to make a big deal in this sense, but you asked exactly the right question, which is, where'd that come from? Right? How did I find this anti-gradient? So that's something we got to talk about now. Okay, so here's an algebraic method that'll do it for you. It's really a very straightforward observation. If you have a vector field given to you, right, if you're looking at a line integral, you will. There's the vector field whose anti-gradient I want to compute. The anti-gradient is the thing whose gradient is the same thing. If I want capital F to be the gradient of little f, then I need that thing on the left in blue to equal to this thing on the right in blue. And notice that an immediate consequence is that I need for the first component to be the x partial of f. Or said differently, I need f, this thing that I'm looking for, my anti-gradient, I need that thing to be the x anti-partial of the first component of the vector field. Right? And then side note, likewise for the other three components, right? So I need this to be this, which gives me that equation, and I need this to be this, which gives me that equation, and I need for this to be this, which gives me that equation. So I have three formulas for f. Now, good news, these are easy to compute. They're just anti-derivatives. Even better, they're anti-partial derivatives, right? I'm undoing partial derivatives, which means just like with partial derivatives, when you're taking an x partial, you get to pretend that y and z are constant. Well, likewise, here, I get to pretend that y and z are constants. Right? So they're easy relatively, they're anti-derivatives with a convenience about them. So that's nice. Here's the bad news. The bad news is I've got to compute three of them. But even worse, f has to equal to all three of these things. If these three things are irreconcilably different, then f needs to be two different things at the same time. It's not possible. Right? And this is the problem that I was referring to here. This is simply not always the case. Not every vector field has an anti-gradient. Times it just doesn't work. Right? So that's the bad news. Now some more good news. Another little bit of good news. I was being a little bit dishonest when I said, compute these anti-partials. Keep in mind when you take an antiderivative, there's always an integration constant. Reminder, quick aside, what's an integration constant? Where does that come from? Well, you see, I just need it to be a thing that when I take a derivative, I need it to be this other thing. So if you put a plus c in there, you take the derivative of that plus c and it disappears in a puff of smoke, and it doesn't change that it still works. Right? So the constant of integration is just anything whose derivative, in going back this way, anything whose derivative is 0. Well, if you're taking partials, what is it whose derivative is 0 when you take a partial with respect to x? And the thing is, it's not necessarily just constants. Now, it could be anything that doesn't have any x's in it. Any function of y and z has that feature. Its x partial is 0. So, good news, bad news, good news. The final bit of good news is, in your attempt to get all of these all equal to the same thing, you have extra flexibility. You're free to add in, as needed, functions of the appropriate two variables that you're not taking the partials with respect to. Right? If with that additional flexibility you can make this work, then you're good. So let's see an example. Here we go. Suppose I'm doing a line integral of this vector field. I want to use the fundamental theorem. Need to find an anti-gradient. in order to use the fundamental theorem? Following the formula on the previous page, well, this first component, I need to take an x partial of that. This second component, well, again, per the previous page, I need to take a y antipartial of that. And likewise, the third component, z antipartial, gives me this. But I do have this additional flexibility. I get to add in any functions as needed, right? I mean, at a glance, look, it'd be tempting to look at these three sort of answers that I got and say, look, these aren't the same. These are different, right? F can't be all three of these things at the same time. That's not the same as that, right? But again, that's not the point. I just need something whose partials appropriately do what they're supposed to do, and all of these over here are freebies. So the question is not, are the things in red equal? The question is, can I use these things over here to make these all equal? And yeah, sure, no problem, right? Just make this, okay, so make this yz, and make the rest of these 0. And now, sure enough, all three of these are the same thing. Everybody good? Okay. So there's a game component to finding antigradients, right? It's, you write down your three starting points, but then you got these flexibilities to deal with. Now, it's not always going to work. Again, sometimes it's a losing game. Sometimes it's tic-tac-toe and you're going second, right? But that will usually be pretty clear if that's the case. Yeah.
So there will be multiple possibilities of the expression of that.
Well, yes, they will differ by just constants, right? So the difference is, if you wanted to make all three of these things equal to a different same thing, you'd have to add the same thing to all three of these, which cannot have any x's in it, and cannot have any y's in it, and cannot have any z's in it. Therefore, it's actually got to be a constant. Yeah. So, but it remains. Yeah, sure. If you want to say plus c over here, yeah, that's fine. But again, you're about to plug in and subtract, so you don't really need. It kind of doesn't matter if you're finding an antigradient. Probably any one will do. Yeah. Right. Okay. Alrighty. So now, can this fail? Yeah. And in fact, this is a nice context in which to bring up these. Y'all remember when we were first introducing vector fields? I said that in some senses it makes sense to Lego together these operators. I mean, they fit, right? I mean, what comes out of the gradient operator is a vector field. Well, that's exactly what goes in the Green's operator, and this actually makes a lot of sense in a lot of situations. And we made the further observation that, well, in fact, these compositions are exact sequences. So everything's got a lifetime of 2. And the fact that in this context everything has a lifetime of 2 gives you an immediate kind of nice thing. Let's ask this question. Suppose I've got a vector field, right? And I would like to know, is there an antigradient? Right? Well, here's the thing. If there's an antigradient, I would need this to die there. Right? I mean, everything's got a lifetime of 2. If it starts on the far left, it's got to die on the far right. See what I'm saying? Okay. Furthermore, let's suppose that I've got a vector field and Green's operator gives you 0. Well, if it dies here, everything's got a lifetime of 2. That means that it was born there. In other words, that vector field does have an antigradient. So, neat little test. Right? I mean, it's kind of weird how this, it fits together just that way, and we already see a connection between the gradient operator and Green's operator. Right? Green's operator is the test for whether there's an anti-gradient. Not zero means no anti-gradient. So, neat trick. By the way, that's for that's in R2. Remember, there's a kind of analogous, fit it together in R3. This being the part of that diagram that we're actually interested in for this moment. And if you have a vector field and you would like to know is there an anti-gradient, then you're going to be interested in computing the curl, and you'd want to know if that's a zero. So again, in this different little piecing together of Lego pieces in this context, but same kind of punchline. In this case, it's curl that is the test. Curl is not zero, then there's no anti-gradient. And here's an easy example of that in action. Example. Now here's a vector field. Does it have an anti-gradient? By the way, you could go through and play the game, but before you even play the game, you can see if the game is rigged against you. Right? That's always a good thing to know. Take the curl here of that vector field. And remember, we have a formula for curl. So there it is. By the way, it's a good idea to know the formulas for these operators. You're going to be using them a lot here and there. So go ahead and memorize those. I think that's a good idea. Right? And let's start to compute the curl. Well, let's see here. We've got to take the third component, R, and take its y partial. And then I've got to subtract. I've got to take the second component here and take its z partial and do that little bit of algebra. And then, etc. for the remaining components. But notice, in some sense, you don't even really have to continue in this case. That first component's not zero. If the first component's not zero, I don't even really care what the other components are. As a vector, this cannot be zero, because the first component is not zero. So as a vector, that's non-zero. So non-zero curl means there's no anti-gradient. And the beautiful thing about this, two seconds. Beautiful thing about this is, now I wrote this down to kind of expand it out and make it more visible, but you don't even have to write stuff down here. At a glance, you can be like, oh, well, I remember this formula. So let's see here, the y partial of that. Okay, well, 2yz plus 1. Z partial of that, 2yz. Those aren't the same, right? The y partial of that and the z partial of that are clearly different. If they're different, then their difference is not zero, and not zero means no anti-gradient. At a glance, yes?
If the curl equals zero, does it necessarily mean there is one?
It does, assuming regularity, all sorts of other stuff that I don't want to get into. But yeah, the one little asterisk I'd put on it, if you want to show that this is in fact the zero vector, then you do need to confirm that all three components are zero, right? It's not good enough for one component to be zero, because who knows, maybe this last component would be 3. And then right. Yeah. So you do have to show all three components. But yep, totally. Yes?
So should we check that there is an anti-gradient before we go using the other formula to compute it?
It's kind of up to you. I mean, I like to just eyeball it. I mean, I would usually not write this down, and it depends on how ugly the vector field is. If it's something that's pretty easy like this, I'd probably just eyeball it and be like, let's see, this. Oh, hey, those are different. And then in order to celebrate what I've shown, I'd probably write down this, sure, right? But if I got zero for all three components, I'd probably just be like, okay, good, I'm going to win this game, and just go ahead and play the game.
Yeah. If it's not zero, then can we just is that the end of the question? There's no anti-gradient.
No, all it means is there's no anti-gradient. Okay. So all that means is you can't use the fundamental theorem of line integrals. It doesn't mean that somehow the question's invalid. I mean, you still need to compute the amount of work that it takes to do the whatever. Yeah, so you just can't use that theorem. Right. Okay. All right. So I want to talk a little bit about this diagram. that I've drawn here. This is not in the book. So again, there's some stuff that I'm going to do in this course that's not in the book, because it's a way of connecting ideas in a way that I think is really helpful. So it's not really new material per se. It's content that I think will help you understand the existing material, right? But so again, I've already made the observation that there's patterns in play here. The several theorems that we're going to talk about in this class, they look a lot alike. They follow the same patterns because, of course, they are ultimately the same theorem, just applied in different contexts, right? So to make that a little bit more visually obvious, right? I'm going to say created these little patterns, which, by the way, I'm shamelessly stealing from if you look at the sophisticated, the high level constructions that go into talking about the generalized Stokes' theorem. I'm just stealing this straight out of there, right? But minus the rigor. So anyway, here's the idea. There are certain kinds of domains on which we're going to be computing stuff. We're going to be plugging functions into points, like so. Right? So no surprise there. We're also going to be doing calculations on intervals. Now, specifically, notice if you give me a function and an interval, I can do this. I can take an integral on that interval of that function. So I'm going to call that a different kind of evaluation. These are the evaluations, and in those evaluations, these are the kinds of integrands that we're talking about. Now, notice also, for your consideration, I can talk about boundaries. The boundary of an interval is 2 points. Right, so there's kind of an arrow going from the right side to the left side. Okay. The calculation that we did with the fundamental theorem of calculus, I just want to point out, this is at the very start of class, first thing we did, we took an interval. We looked at it. Here, let me do it down here. We took an interval. We looked at its boundary points. We looked at this expression, f of b minus f of a, and then I made the seemingly odd goal of I would like to compute that as an integral, and through an argument, we came up with this idea that, well, if you were to take the derivative and then do, this evaluation of that derivative function on your original interval. So if you were to compute then like this, then you do get, indeed, an integral, which is equal to the original thing. Right, so this just as a kind of what we call a diagram chase, I just want to point out that this is kind of one way to think about what we did, that we took a boundary, we found a corresponding operator, such that that evaluation becomes that evaluation. I just want to point that out as a cosmetic, very superficial. This is just kind of how the objects in play kind of lay out on the page, and a sort of a geometric-ish, pattern of what happened. And now let's talk now about the fundamental theorem of line integrals. This will be our last thing. Super quick. I apologize, but real quick. On curves, we can do line integrals of vector fields. Curves have boundary points. And what we made, the argument that we made is we started with a curve, we looked at its boundary points, we evaluated like so, we then asked, can I think of this as an integral? Namely, is there an operator that I can apply? Yes, gradient operator. To where this evaluation gives me the same thing. And that's exactly what we argued. Right, so notice that the pattern of the argument is the same. So, let me not use red, that's aggressive. That and this give you evaluations that are the same. So the pattern of the fundamental theorem of line integrals The pattern of the fundamental theorem of calculus, same pattern. And the reason this is important for me to point out, for y'all to notice, is that we're going to find that in other contexts. We're going to find that there is a way to relate let me do this with a different colors. Way to relate double integrals to line integrals by doing the same sort of thing, and it's called Green's theorem. And there's a way to relate triple integrals to surface integrals by doing the same thing. That's called Gauss's divergence theorem. And there's a way to relate flux integrals to, we haven't defined those yet, but a kind of a thing called a surface integral. We can relate that to a line integral by doing an analogous thing. It's called Stokes's curl theorem, etc. So this pattern that we see here is the first of many examples of this kind of an argument. So I like to make a big deal and point it out. The purpose of these diagrams, again, not in the book, is to help you notice how dramatic these patterns are, right? And so anyway, I'm going to be making lots of references to these diagrams as we go through the rest of the course. See y'all later. Thanks for sticking around for an extra minute. Don't forget to turn in your homework right up here at the front, as usual.